Avishai Wagner, applied research scientist from Intel IT AI Group. He will be talking about using AI to increase hardware performance. Thank you. The stage is yours.
Okay, can you see my screen? Okay, great. So, hello everyone. My name is Avishai, and today I'm going to talk about how to using AI to increase hardware performance. This work is done by at Intel, by my group at Intel IT Artificial Intelligence. Our group has over than 200 AI professionals, and our main mission is to transform intercritical work using AI. This includes sales, product engineering, manufacturing, or in my case, process architecture. And this really, I'm going to talk today about process architecture. So, first of all, some background. Is when Intel is working to improve CPU performance on a yearly cadence. Each new product should be at least 10% faster than previous product. And one of the ways to do it is to allow the system to consume more power. However, performance is not the only thing that matters. We also care about, for example, battery life. It's nice to have high performance, but if your battery will end in 5 seconds, this product doesn't worth really too much. And there is a trade-off. For laptop, more power will result in shorter battery life and thermal challenges. So more power is more performance, but shorter battery life, and your computer will be really hot. Okay, so it's really not a good thing. So how can we balance between battery life, thermal budget, and performance? And how machine learning can help us solve this problem? So today I'm going to focus about the trade-off between battery life and performance, and less on thermal budget, although thermal budget today is really important part of the equation. So let's go directly to the end, to production mode, and we'll try to explain how this all this process works on your computers. So we have something that's called workload classification prediction, workload classification engine. Every constant time period, we get some system data. It can be power, it can be the temperature of your computer, fan speed, some data from about the memory of the computer. And we take all this data and give it as an input to some classifier. This classifier returns, predicts one of the following workloads: idle, battery life, bursty, or sustain. Each workload actually represents the amount of processing your computer is given to do at a given time. At idle, your computer is really doing nothing. Okay, no tasks at all, power is really low, and there is nothing to do. In battery life, power is also relatively low, but your processor actively performing a task in the background. It can be when you're watching a movie, or if you are on a video call, something that called video playback. Okay, so in this case, you are on battery life. The third workload is bursty. In bursty, most of the time your power is also not too high. However, burst of activity interrupts these periods of idle or battery life, okay? And this burst really short and have really high power. They really heavy to compute. Okay, so you can think if you are working with Excel, for example, most of the time you are not doing something that really heavy, but sometimes you need really short, for short time, high amount of power. And the last workload is sustain. In sustain mode, power is really high all the time because you are doing heavy compute for long time, deep learning run or rendering an image and things like that. So after our classifier predict one of the following workload, some parameters in your computer dynamically adjusted. It can be power setting, system setting, or hardware setting. For example, if we are on sustain mode, performance is more important. Okay, we want our computer to work as fast as possible. So we allow the system use more power. But if you are on battery life, if you are watching a movie, more power really will not improve your user experience. However, it will make your battery life really shorter. So we force the system use less power than it wants. Okay. So now after we understood we understand the workload classification engine, let's go into the detail of how we build the model. So the first step and the most obvious one is of course data collection. So what data would we use? Multiple applications will run on real system with Intel CPUs. And this application, according to Intel at least, represent real-world behavior such as Office for bursty, gaming for sustain, idle for idle, and video playback for battery life. And of course, we have more applications that are combinations of these all 4 workloads. For each application, hardware data or telemetry, system data as I said before, was collected every constant time period. So after we collected the data, we need to do the labeling, okay? So it's nice to have 4 workloads, but these 4 workloads are not dog-cat problems. There is no real definition to sustain, battery life, bursty, or idle. We need to do the labeling by ourselves. We can't give it to some random guy and ask him to label this sentence is happy, sad, this image is dog, cat. We need to use more smarter method. So what can we do? So the first thing and the most basic one is some business understanding rule. Some applications are known to be more sustained because performance is more matter, like gaming, and other more battery life, like video playback, as I mentioned before. But more than applications, we practically know how features should behave in different workloads. So what leads me to the next types of methods, which is clustering. We can cluster the data set and discuss with professionals how each cluster should be labeled. For example, if we have cluster that the sample there characterized with high power on average, it probably sustain. And if the average power is low, is more battery life. If the variance of the power is very high, it's probably bursty, okay, because power in bursty is really low and then jump to really high. So we can give label to the cluster after, like we can give label to the cluster. Okay, the third and final types of method are weak supervision method. Okay, we can provide a set of weak rules and use generative model to combine them together. To who of you are familiar with Snorkel, for example, we can give there lots of labeling function based on our business understanding. As I mentioned before, we know how the power should behave. This application should be sustained or battery life, and we can combine them together with some machine learning models. So after we did our labeling, we go into the phase of building the model. So this is pretty straightforward, but I want to talk a little bit about the challenges in building our model. So the first main issue in this problem, in the whole problem that my team is working on, is the size of models. Large models can consume too much computation for calculation and are too large to fit in size constraint. Okay, we need to put this model at the end in interprocessor, and there is not lots of room there. And large models also damage performance. I can't put GPT-3 because GPT-3 is really take long time. So we must use small models like linear models or trees. And this requires from us lots of pre-processing. Okay, we must to prepare smart feature and do lots of feature selection and extraction and pre-process that you are familiar with. The second challenge is prediction on idle. On idle, the system should do nothing, and that includes our model. Okay, and linear model is small, but still something. So we need actually to do really fast heuristic, something that really like if else, and to detect idle as soon as possible. And the last challenge is how we don't change workload type too frequently. If we are switching from sustained, bursty, battery life, idle 4 times in 4 seconds, it's not really that logical, and it's also damage also can hurt the performance of the processor. Okay, so we must do some post-process stage for smoothness, like change prediction only if the probability of the new workload is high enough compared to the previous one. That's why we are not going from sustained to bursty to battery life too much. We don't switch the workload too much. Okay, so how actually do we evaluate our model? So the first metric and the most basic one is hit rate, okay, or accuracy. Of course, we want the accuracy to be as high as possible compared to our label. But to notice is that different errors matter. If the real workload is idle and my model predicted battery life, it's not that good, but it's fine. But if my model predicted bursty, the damage on the real performance can be really, really high. The second metric is new class detection pace. How soon did the model detect a change in class? So it's nice that the accuracy can be very high, like 95% correct. Our model can be 95% correct. But if we are moving from battery life to bursty and we miss this switch in few seconds, 2 or 3 seconds, the punishment in real run can be really, really, really high. Okay, so we must detect changes as soon as possible. The third metric is prediction stability, and I talked about it minutes ago. How often does the model identify new class? We don't want to change between classes too much, and there is a trade-off between the new class detection pace and the prediction stability. We want to detect as soon as possible, but we don't want any false alarm when we are switching between workloads. But the really, really, really only important metrics for our needs is simulation, performance, and battery gain on real run. So we use all this metric to decide which model we want to send to simulation, but at the end, our results only measured on simulation, performance and battery life with workload classification versus without it. And simulation can be really expensive, so we can't send any model to simulation anytime we want. And sometimes we send our model to simulation and we see that part of the assumption we assumed at the beginning wasn't right. Okay, we even can change our labeling. There are places that we thought at the beginning should be bursty, and they are more, and we now change them to battery life because we see the battery is more important than performance in this area. So this is the really at the end the only and most and only important thing. So the results are pretty nice at the end. Some example, and video playback, when battery is important, we earn back up to 1 hour of battery time. Okay, so if you are watching a movie without a charger next to you, you have 1 more hour before your battery will end. When you are doing some things that related to sustained workload, like rendering an image, we gain up to 10% performance. And where you are doing a burst related thing like Office, we gain up to 1.5% performance without losing any battery life at all. And remember that 10% is the difference between new products. Okay, new product is 10% faster than previous one. So 10% improvement on sustained mode and 1.5 on bursty really help us in order to give new products. So to summarize, this workload classification improves both performance and battery time. It's very easy to understand. I didn't talk about it, but it's really important part of this whole this whole project is that it's easy to understand, required lots of work on labeling and evaluation, and on your computers right now. Next steps is how we want to use it for more use cases and discover new type of workloads. So this is it. Thank you very much. And if you have any question, I will be happy to answer.
Thank you very much. It was super fascinating to see how you need to be very sophisticated with what you are doing. You need to find the balance. So I have another question for you. Did you try to optimize performance directly on laptop instead of using workload classifications?
So we actually trying to optimize performance and battery in different use cases we have, but in these use cases, it was very important. It will really be easy to understand because we want to sell this to as much as people as possible, and they need we want them to use this workload classification for their needs, okay, not for our needs. So it was really important part of this problem. So but on different cases, we really try to optimize performance on battery.
Okay, interesting. Another question: does the model work on the same or different type of machines?
Okay, so on different computers, the workload can give different results. Okay, if you have Dell machine or HP machine, sometimes the results can be different. But in general, the model is pretty robust. Okay, sustain will be pretty similar on most of the computer. In new generation, new product, we of course must retrain and do this whole process again, but so it's work a little bit different, but it's pretty robust.
Okay, interesting. Very interesting to see the difference. Thank you very much.